Hi everyone, am I audible? Hello, am I audible? Is it fine now? It's fine, right? Like, can I get a yes or it's fine? Hello. I think there is some issue. Is my voice audible right now? Okay. Let me make it full screen. Is it fine now or is it gone now? It's fine? Okay, great. I think we can begin then. Yeah. So as I said, we started like we wanted to start searching today. That is what we are going to do. Uh, so before we begin, did any of you try out some linked list questions? Yes, no. Okay. Shadab did. Anyone else who's tried? Okay, great. So just keep on practicing. I think that is equally important. So let's start with searching. So I'll quickly explain the binary search algorithm. So that is not the only algorithm in searching, but that constitutes the major part of it. So I'll stick to that for this particular lecture, I think. So let's say we are given a sorted array. and we want to find any single element in it. Let's say I want to find 3 in this particular array. So one simple thing that comes to the mind is, let's look at all the elements one by one. So I'll compare, is this 3, is this 3, and so on. Does that seem like a possible solution? Running a loop, checking if it's 3, and if it's 3, then answering yes, otherwise no, right? So that simple algorithm is called a linear search. So we are going linearly over the array and checking if any of the elements is 3. If it is, we'll print yes. Otherwise, if we reach the end, we'll print no. Okay. I hope everyone can implement this for loop of linear search. Will you all be able to implement this? Can I get a yes? A simple for loop, checking if it's 3 and printing. Okay. What is the problem here? Can you tell out the time complexity of this linear search? Right. Essentially, it is ON, because in worst case, your answer could be at the end or could not be present. So you are going to go over all the elements, which is essentially ON. Okay. So people have come up with another algorithm, which is called as binary search, which helps us quickly get to an element if the array is sorted. So important condition, if my array is sorted, then I can in fact go ahead and do binary search here. What is binary search? I don't know how many of you were there in my first class. I gave some kind of an example for it. So let's say you are searching in a dictionary. You don't directly go word by word, right? What you do is you open it in the middle and then see, do I need to search on the left or do I need to search on the right? So same idea can be used here. What we do is we find the middle, which is 6. I want to find 3 and the array is sorted. Can I ever find my 3 in this portion of the array? What do you think? Why? I don't know what is there, right? Imagine that I don't know the array as well. I just know that wherever I landed in the middle, it's 6, right? You don't know what is here, right? But the array is sorted. You still can't find it like beyond 6 because the value is smaller than 6. It's not even possible that it will be present there if the array is sorted. It must be present on the left side. So that is exactly what you do. You say you will change your maximum to mid -1, that is this, and you will only search in this remaining domain. Does that make sense to everyone? That I only search in the left half now, and you will use the same idea. Find the middle, check if you want to search on left or right, and go according to that. So if I have to like say how we are doing this, can I say that initially we had a search space of n, we found the middle and then chose one of the two sides? That is, can I say after one iteration I will be left with n/2 amount of elements, or n/2 search space, half of the search space? Yes or no? Like either I'll select left half or right half. If this is 6, I want to search 14, I will only use the right half. If I want to search 1, I will only use the left half, right? But essentially, I'll only be left with one of the two halves. So it will become half. Can you extrapolate and put out the next step? After I do the same with this n/2, that is find the middle, what will be the search space left after I select one half? n/4, right? So as an example here, okay, 3 is here, but let's say 3 was not here, but it was, let's say 2. Now if you are finding 3, you will find this 2 and say I'll go to the right. So again you divide it into two halves, 1 and 4, and select the right half. So essentially what you are doing is reducing your space by half, half, half till it's a single element. Yes or no? Do you agree with this? You're reducing by half, reducing by half, reducing by half till it's a single element. So let's say after k steps, it becomes a single element. Can I say the number of steps I get is log base 2n? Yes or no? Simple maths. I'm saying we'll keep on dividing by 2. So 2's power piles up, 2, 4, 8, 16, and so on. So after k steps, it will be 2 to the power k. So after k steps, if the number of elements become 1, I need to stop, right? So n by 2 to the power k is 1, n is equal to 2 to the power k, or k is log base 2n. So after log base 2n, I will stop. Either I would have found my answer, or the answer is not present. Like I would have got a conclusive thing that is the answer there or not. Is this making sense to everyone? Yes or no? So that is why the time complexity of binary search becomes log n instead of it being on, right? And log n, as you can see, is very, very less than on. Is this much clear to everyone? Okay. Anyone with any doubt, let me know. Will there be log n or 1 plus log n? That's immaterial. Like time complexity wise, it's log n. That totally depends upon how you implement it, right? How many ifs you write. I can write more and then it will be more. So that's not defined actually. Plus 1. Okay. So you all take a moment and try to write the binary search algorithm. Then I'll also write it down here and clear out some doubts, that some mistakes that people make while writing binary search. So if you can quickly try to get a copy pen and try to implement it on your own, that would be a good idea. It's a relatively simpler algorithm. That's why I'm telling you can try to do once. Anyone who could write it down? Okay, let's do it together. So what all do we want? We want first our search space. I have this much space to search. So we call two variables here, lower bound and upper bound. So we represent it with L and H, low and high. So I'll use the standard annotations. So lower bound of my array is 0 and upper bound of my array is n minus 1. Can everyone see this part of the board? I hope it's visible. Where I'm writing partial. Okay. I think this would be visible then if that was partial. Right? Okay. So we have our L, we have our H. What is the first step? Find the middle and check, right? Okay. And we have to do it in loop. So I'll not write the loop for now. But essentially, what are my 3 steps? I want to find the middle. Then I want to check if this is the answer. If this is the answer, we have found the element. Otherwise, I need to shorten my range either to this or to this. So let's write that down. So mid equal to L plus H by 2. Find the middle, L plus H by 2. Then if A of mid is only your element that you need to find, let's call it K for now, then you just return mid, right? Not to be confused with number of steps, I'll make it something else. Okay, so if I found the element that I needed to find, I'll simply return. Otherwise, if my value here is more than the element that I need to find, so mid is greater than F, which half should I go to? Left or right? Think and then tell. People get confused. F is smaller. That means you will need to search on the left, right? So what I'll do, I'll say H now becomes mid minus 1. This is our L now, this is our H. So H equal to mid minus 1. Otherwise, L equal to mid plus 1. That is, this becomes here. Is this idea making sense to everyone? Steps of binary search, yes or no? What should be the loop? When do we need to stop? L less than equal to H. Okay. So many people get confused here whether to use less than or less than equal to. Let's use a simple rule of thumb. Let's see what happens when L is equal to H. Okay. Let's say L is also here, H is also here. Can I still say 15 is not checked? Remember what is happening. If let's say L was here and H was here, I would have checked mid and I want to go right. So I will do L equal to mid plus 1. Right? I'll explain it again. So let's say we have 8, 9, 15. This was L, this was H, this was mid. Right? Let's say I was searching 15. So when I look at mid, I will say L will become mid plus 1. L also becomes this. Yes or no? So if I stop when L becomes equal to H, right? So those of you have written while L is less than H, that means you will stop as soon as L becomes equal to H. Then you will miss out on checking 15. Can you all see that? Yes or no? You will not check this, right? Otherwise, you will need to write an extra if here. Generally, in an algorithm, we don't want to do that. So basically, I will write L less than equal to H. Even when it's equal, we are still left with checking that particular element. We need to check that. So we'll do mid. It will be the same element. We'll check it. Now, if one of these two conditions happens, that means we can't find an element. So we can say here return -1. We couldn't find anything. Does that make sense to everyone? Why we need to do L less than equal to H? Others? Yes, no, the simple case. Okay. Just type in a repeat. I see very few yeses. So if you are confused, let me know with a repeat. Okay. Cool. If it's okay, then what you can think of this is a template. how does it become a template? Whenever you have to do binary search in whichever question searching, whenever you have to do binary search in whichever questions, these are the things that you need to take care of. You need to initialize L and H perfectly. That is initialization. This will always remain the same. This will always remain the same. Here you will have a condition to check if your mid is answer. And then here you will have your propagation. That is, if this condition is not satisfied, which conditions will make me move towards left and right. So just three things that you need to change in this template: initialization, check for the answer, and then propagation, whether I want to go left or I want to go right in all the binary search questions. Is that okay? We'll take up one or two examples and we'll see how it works. But does that make sense? You don't need to touch the remaining part in most of the cases. This mid calculation, this while L less than equal to H, and so on, right? You just need to touch this condition, this condition, and these two. That's it. And everything will work as it is. Okay. Let's take up one or two questions and see how we are able to implement this template there. So those of you who attended the first lecture would know that binary search is not necessarily only available for sorted array. It's more like if there is a separating condition. So let's talk about that separating condition also a bit. So I'll take up a problem and then explain the separating condition. Let's say we are given two arrays, array 1 and array 2, with distinct elements. And we also know that array 2 is formed by removing exactly one element from array 1. So as an example, let's say array 1 goes like 2, 4, 3, 7, 11, 8, right? Let's say I decide to remove 7 from here. So array 2 becomes 2, 4, 3, 11, 8. Does that make sense? What is array 1 and array 2? So array 1 is a general array. Array 2 will be formed after removing exactly one element from array 1, and it has distinct elements. Okay. So what you need to tell is you need to find the element which was removed. So your question says find the removed element. Okay. First of all, can everyone come up with a linear search? How can we find the removed element in linear search? Two loops. How many of you agree with two loops? One loop here, second loop here to check if that element is present or not. Okay, one loop also, Surya. One loop how? XOR of both. True, XOR could also be a possible answer. Iterate array 1 and compare. Exactly. We don't actually need XOR here. That's overdoing stuff. If we carefully look at it, elements will be same till they are not. And when they are not, that means this one was missing. Can I say that? Yes or no? It could simply be for I equal to 0, I less than array 2 dot size, I plus plus. If ever array 1 of I is not equal to array 2 of I, that means array 1 of I was removed. Yes or no? Order will be same, right? What did I say? Array 2 will be formed after removing an element from the array 1. So if I remove this is what will be there, right? Yeah. So order will has to be same. So what I was saying is, what we can simply do is just iterate. As soon as there is a difference, that means that particular element was removed and I can return it. If complete array 2 is same, what does that mean? What will be the corner case? If complete array 2 for complete length of array 2 elements are exactly same. Yeah, last was removed, right? Last one would have been removed. Can you see that? So you'll say return array 1 of array 1 dot size minus 1. Is this idea making sense to everyone? Yes, no. Just type in a repeat. I'll repeat it. I see very few S's. So not sure. Anyone with the repeat? Please repeat. Sure, I'll do that. Did you understand the question first? You are given an array. You are removing an element. When you remove this element, you get 2, 4, 3, 11, 8. This is the second array. Does that make sense? So you're given two arrays. Second is formed after removing one thing. We don't know what from array 1. We need to find what was removed. Is the question okay? You can type in yes, so it would be good. I'll proceed. Okay, cool. So then what I'm saying is, what we can do here, if we carefully see, the elements will be same till we reach the element which was removed. Do you agree? This is equal to this, this is equal to this, this is equal to this, till it's not. When it's not, that means that was removed, right? Because this will now match with the next one. Do you agree with this? As order is remaining the same, that is what will happen. So that is exactly what I have written here. I am iterating. When it becomes not equal, that means first one's element was removed. So I have returned array 1 of I. Is that clear? If everything matches, if everything in array 2 matches, that means it would be a case like when I remove this 8. So first array will be 2, 4, 3, 7, 11, 8. Next one would be 2, 4, 3, 7, 11. So this matches, this matches, this matches, this matches, and this matches. That means last one is extra, which was removed. Is that okay? So that's the corner case. Cool. So moving on. This is a linear search solution. What would be the time complexity of this? No, we are iterating till array 2 dot size, right? Can you see that? Yeah. So what will be the time complexity? Obviously, it will be O(n), because we are going through the array, right? Okay, let's do something better. Can we do something better? Which element is removed whose right side is not equal to array 1 and whose left side is same in both the arrays, right? Great. So now comes the part of separating condition. So what is a separating condition? Something which helps us distinctly determine if we are at a random position, are we on the left side or on the right side of the answer? So as an example, let's say I don't know this array and I just land on this 4, this position 1, and I see both are equal. Can I predict whether my answer would be on the right side or the left side? What do you think? If I don't know what this is, I just know that these are equal, array 1 is equal. Can I predict whether my answer would be on the right side or on the left side? Yes, it would be on the right side. Can everyone see that? Yes or no? That it will be on the right side. Why? Why will it be on the right side? Because it still matches. The elements still match. Can you please repeat the problem statement from the start? Current one. I'm not able to get you, but okay. Problem statement was that you are given one array, remove one element, you find the second array, right? And you have to find the removed element. Is that clear? Then we came up with this ON. Now I'm saying that separating condition, right? I was talking about separating condition. Separating condition is what? If I give you a random index and you are allowed to query certain things from it, will you be able to determine if I am on the left side of the answer or on the right side of the answer? So if I give you a random index 1 and you ask me if they are equal, right? And I tell you, yes, they are equal, then can you be sure that your answer will be on the right side? I'm saying yes, because if they match, that means nothing was removed till this point and only an element was removed from the right side. Does that make sense? Right? Similarly, if you are at this place and you ask me, are they equal? And I say no, that means answer was on the left and we have passed it. Can I say that? And I need to search on the left. So for binary search, sorted array is not important. What is important is a way to distinguish whether you are on the left side of the answer or on the right side of the answer. Does that make sense to everyone? Yes or no? Okay. So how will you go about it? Let's look at it. What we will change? So L will be still 0, H will be still n minus 1. So array 2 dot size minus 1, this thing. So let's do that. While L less than equal to H, mid nikala, like you calculated the mid, L plus H by 2. Now, how to check if current index only is your answer, right? In simple binary search, it was easy. If my current element is same as the element that I wanted to find, that is my answer. But how do we determine if this is the answer itself? Can you all think and tell? How do we determine if your mid element itself is the answer? Why are we running on array 2? We'll be running together on the indice. We are not running on array 2. It's just that we are fixing it to array 2 dot size because we can't run till here. What if there is a out of bound situation here? Can you see that? Yeah, so that's why we are running only till here, because this is the corner case. If we don't find anything in the binary search, we'll return from here. That this was my corner case. Is that okay? Yeah. So can everyone determine how do we tell if this is the answer only? It's first number equal index if mid minus 1 is equal. Exactly. So if previous value is equal and current value is unequal, can I say this first one is the answer? Yes or no? Let me write that down. So if previous value is equal, that is array 1 of mid minus 1 is equal to array 2 of mid minus 1, previous value is equal, and array 1 of mid is not equal to array 2 of mid. That means array 1 of mid is your answer. Yes or no? Do you all agree with this? If previous is same, next is not same, that means this one is your answer. Everyone? Okay. Let's look at when we want to search on right. Mid minus 1 can get out of, I'll talk about that. Yeah. So let me follow the flow and then I'll talk about that. Let's say when will we go h equal to mid minus 1? When do we want to go only search on the right? Can I say when at mid they are equal? That means anything on its left is not useful. So if array 1 of mid is equal to array 2 of mid, that means they are equal. I want to search on the right side. So I will do L equal to mid plus 1. Otherwise, h equal to mid minus 1. Does this idea make sense to everyone? So if on mid it's equal, that means search on the right. If on mid it's equal, search on the right side. If on mid is not equal, that means search on the left side. These two conditions. Yes or no? Others, I got just 2 yeses. Others, what are you thinking? Does this make sense? You can type in a no or repeat if you want me to repeat it. Okay. Cool. Then the condition that Tanush was talking about, that when we do mid minus 1, immediately an alarm bell should ring in your mind that can it go out of bound, right? As soon as you type array of mid minus 1, mid plus 1, mid plus 2, mid minus 2, any complex situation, can it ever go out of bound, right? That is the first thing that should strike in your mind. And here, for the fact it can, what if mid is 0? When L is 0, H is 0, mid will be 0. And if I check this, it will be out of bound. So you need to handle when mid is 0 separately. So let's see what will happen. When will that happen? That will only happen if the first element was removed. Can you all see that? Only if the first element was actually removed, then you will land in this situation. So you can check it outside if you want, and then start with L equal to 1. That is, remove that threat altogether, saying that I'll check 0 beforehand. If array 0 itself is not equal, that means first was removed. And then I'll only start searching for L equal to 1. Does that make sense to everyone? Or if you want, you can add an extra condition here. I generally don't like to touch this, and whatever is out of this, I just put it outside. That I'll not touch this. Okay, because I know this will work if bounds are okay. Cool. So that's about, then from lower equal to 1. Yeah. So we'll start at L equal to 1 with extra check here that if first element itself is not equal, that means this is your answer, which was removed. So that you can check separately. Okay, great. I think this is clear to everyone. So what we will practice now is looking at certain different cases and figuring out if we are able to get the separating condition fine. Okay. So I'll quickly give a few more questions and you guys should think and tell, can you find a separating condition? Okay. Next question goes like this. Let's say we are given an array of size n, which is of a format of a mountain array. So what is a mountain array? There will be a few elements which will first increase, then decrease. So as an example, if I have something like 1, 2, 4, 6, 10, it increases, then it goes down. Like let's say 8, 7, 5, 3, 1. Okay. It first increases, then it decreases. Then this is a mountain array. And what you want to do is you want to find the peak in it, which is 10 here. Does the question make sense? So there is an array where values first increase, they reach a peak, and then they go down. This peak could be on the corners as well. For example, if it's only an increasing array, then last one is the peak. Or if it's only a decreasing array, then first one is the peak. These are possible corner cases where first or last is the peak. But in general, there will be an increasing part and a decreasing part. Is the question clear to everyone? Yes, no? Okay. Let's think, what can we do? So generally your linear search directly will tell you the separating condition. Generally that happens. So if you can think of a linear search solution here, that is a simple loop solution, then you will be able to easily get the separating condition. Right? Great. So can anyone come up with a linear search solution here? How can we, with a loop, find the answer? Yes, maximum number will be peak, right? But can we do it in a lot better way than that? Like for maximum, you'll have to go through the end of the array. Can we find a way where as soon as we land on the peak, we say this is the peak? Can there be a way like that? Right and left both are small. Great, great. So if you carefully see, this increases, right? So for any element, previous will be smaller, next will be greater. Do you agree with this, everyone? First half is increasing. That means for every element, it's like previous will be smaller, next will be greater. For 4 also, previous is smaller, next is greater. 6 also, previous is smaller, next is greater. Can you all see that? That's the meaning of increasing, right? That for any element, next is greater, previous is smaller. Yes or no? What if we have 2 10s in the array? That's given in the question. Like probably you can assume that it will that kind of thing will never happen. Okay, because it will have a single peak, then there are 2 peaks. That does not make sense. Is that okay? Is everyone able to see this idea that any element will be having next as greater, previous as smaller, next as greater, previous as smaller, till we reach the peak? What happens at the peak? Next is also smaller, previous is also smaller. Yes or no? Everyone? And what happens after the peak? Let's look at that as well. Previous is greater, next is smaller. Previous greater, next smaller. Here, previous was smaller, next was greater. Can you see the separating condition which happens? Yes or no? So on the left side of the peak, you can choose one of the two. Previous will be always smaller. And on the right side of the peak, previous will always be greater. Let's forget about next. We just need one to check. We don't need both. But ideally, you can also do with the next. Like it's your choice whether to use previous or next. I'll use previous for this case. So if I land at a random element and see that previous is smaller, that means I would know I need to climb up and reach the peak. So I'll say L equal to mid plus 1. But if I land somewhere where previous is greater, that means I'm on the downhill. That means I need to search on the left side. So I'll say highest is equal to mid minus 1 and find the peak. Is everyone able to understand this idea? How we will be able to get the peak with the separating condition? Okay, let's do one more quickly. I'll not write the code for this. You can try it out, but it will be easy. Like you don't need to do much. For checking the previous smaller, just do array I is greater than, sorry, array mid is greater than array mid minus 1. Then mid minus 1, there are conditions with 0th element, which you can handle separately. Cool. One more question goes like this. Let's say we are given an array of size n, which have all the elements in consecutive pairs. So all elements are like consecutive pairs. Except one. So as an example, the array might look like 2, 2 consecutive pair, then let's say 6, 6 consecutive pair, then 4, 4 consecutive pair, then let's say a single element, then let's say 5, 5, 10, 10, 12, 12. So consecutive pairs, one somewhere will be alone. Is the array form clear? All the elements occur like consecutive pairs except one element, and you need to find that element which is not with the consecutive pair. Is the question clear? One more thing here is, it will never happen that there are 4 together. For example, it will never happen that 6, 6, 6, 6 is there or 6, 6, 6 is there. They will always be in pairs, right? And then a new element will be there. Is the question clear to everyone? Yes or no? Elements are in consecutive pair except one. You need to find that single. Okay. Take a copy pen. Try to see if you can find some separating condition here. XOR is 1, but again it's ON. Can you see that? XOR is obviously right. When we do XOR, it's ON. But we need to do binary search. We need to go to login. So can we find some separating condition here that separates it out? Great. Oh, two of you have figured it out. That's awesome. So if we look at the indices, seven, 8, 9, 10, 11, 12. When we are on the left side of the answer, indices of the pair are even, odd. Even, odd, even, odd. Right? As soon as we go and skip this single, the parity will change. That is, now it will be odd, even, odd, even, odd, even. Can everyone see that? How the pattern changes on the left and right. Here it's always even, odd, even, odd, even, odd. Till we waste on a single element are even, and then it always becomes odd, even, odd, even, odd, even. Can you all see that? Even, odd versus odd, even here on the right side. Yes or no? So this will determine our separating condition. So if you land on the left side and you are on an even, then you will check, is the next one also same? If it is, you would know that you are on the left side. If it's not, that means essentially you are on the right side, because you are on an even and you found the next and it was not the same. That means you are on the right side. So simple odd even idea can help you find the separating condition here. between left side and right side. Are all these variations clear to everyone? So as I said, it's not about sorted array, it's about separating condition. Is that clear to everyone? Can we move on? Please repeat this logic. Sure, I'll do that. So try to, I'll repeat the logic again. Try to recall the indices, right? So array indices start from 0, assume, right? So when it's a pair, can I say it will be 0, 1, which is even indice, then odd indice. 0 is even, 1 is odd. Do you agree? Then it will be 2, 3, which is again even, odd. 4, 5, which is even, odd. So till there will be only pairs, it will have to be even, odd, because they are coming in pairs. As soon as there is a single element, we waste an even there, and then it starts odd, even, odd, even, odd, even. Like, are you able to understand that? So it's always even, odd, even, odd, even, odd, but because of that single element, the switch happens. It becomes odd, even, right? Okay. So that could be the differentiating factor between them. Cool. So I hope everyone is clear with the separating condition idea and can try out some questions on this. I'll take up one more interesting pattern here in searching, not exactly binary search, but it's a common question. So I think I should cover it. So question goes like this. Let's say we are given, okay. So I think I forgot one particular pattern here in binary search. Let me cover that first. So binary search a lot of times is used in combination with other things, right? So as an example, it need not necessarily be that it's just searching a particular element. So as an example, I'll take a question. So let's say we are given an array of size n, and we need to check if there is a pair of 2 elements in it whose sum is k. So as an example, if I have a sorted array, actually sorted, and I want to check if I can find 2 elements from it whose sum is, let's say, 11. Okay. So given an array, can we find 2 elements whose sum is 11? 2 pointer is right, but how do we arrive at 2 pointer? That is an interesting fact. So probably that will help a lot. Here, there is an answer, 9 plus 2, 11. Do you all agree with this? So given an array, you have to find 2 elements whose sum is your given element, 11. So here we have 2 elements, 2 plus 9, whose sum is 11. So it's there. Okay, what would be the absolute brute force of this? Right, absolute brute force would be 2 loops, right? I simply write for I equal to 0, I less than n, I plus plus, for j equal to I plus 1, j less than n, j plus plus. If they become equal, array I plus array j becomes equal to sum, you return pair of ij. Do you all agree with this? Simple, 2 loops. First loop, fix an element. Second loop, fix the second element. Check the sum. If it becomes s, that is your answer. Right? Everyone agrees with this? Okay. This is a simple thing. Like if you're not getting this, probably you need to revise basics. I think this is a very simple thing. Okay, moving on. Can we improve it? So answer is yes. Some of you are also giving that we can use binary search here. So that's perfectly right. How can we use binary search here? Let's look what we are doing here. I'm finding this J such that array I plus array J is S, and it's a sorted array. So why am I linear searching on it? Let's look carefully. The element that I want to find is nothing but S minus array I. Can you all see that? Array I plus array J is S. That means array J is S minus array I. So basically what I'm doing with this loop is trying to find such an array J whose value is this. I can simply do this with the help of binary search. Why do I need a linear search here? So that is exactly how we can improve it. What we can do is we'll run for I equal to 0, I less than n, I plus plus. You have your array I. Then you say your element to find becomes S minus array I. Now you know what you need to find in this sorted array. And then you can apply a binary search instead of this linear search. Is this idea making sense to everyone? So essentially what I will do is I'll first fix 1. I want to get 11. I'll do 11 minus 1, 10. Can I find 10 in the remaining array using binary search? Answer is no. Then I'll look at 2. I'll say 11 minus 2 is 9. Can I find 9 in the remaining array using binary search? Answer is yes. So I get my pair. Is the idea making sense to everyone? How we can go about using binary search here? So instead of this linear search, we replace it with binary search. Others? Yes, no. Repeat. Sure, I'll happily repeat it. Did you understand this brute force? What we were doing? Running 2 loops, fixing 2 elements, checking their sum. That was clear? Right, that was clear. Okay. So I'm saying, what are we doing here? Let's look at this. We are finding one element, second element whose sum is this, right? Do you agree, Dheeraj? Essentially, we are doing this, right? So if I fix one element, can't I say the other element is just S minus array I? Yes or no? Do you agree with this? So if I am running the first loop, which fixes my I don't need to run a second loop. I can simply calculate the element that I want to find now is S minus array I and binary search it on the remaining part because array is sorted. Are you able to understand that? So this second loop will no longer be a loop, but it will be a binary search thing. Yes or no? Because I have my F that I need to find. So it's like I'm saying, let's first fix first element as 1 and do 11 minus 1, 10 and try to see if we have 10. Then fix the first element as 2, do 11 minus 2, 9 and try to see if we have 9. And 9 will binary search. Okay. Cool. So initial approach was n square because we were having 2 loops. Now we have improved it to n log n because we know earlier it was linear search, so it was n into n. Now it's binary search, so it's n into log n. Does that make sense to everyone? Why it's n log n? Because we have replaced this n search with log n search or binary search. That is the only thing that we have done. Yes or no? N log n. So I want to lay down the foundation to a very important concept from here. So if this much is clear, let me know with a yes. Then we'll move on. Okay. So this is n log n. Many of these solutions can improve even further from n log n using a technique which you would have heard called two pointers. But let's understand when two pointers is actually useful. Okay. So let's look at it this way. When my first element was 1, what did I need to find? I needed to find 11 minus 1, 10, which would have lied somewhere here. Do you all agree? If it was there in the array, it would have lied somewhere here. Everyone, do you agree with it? One's pair to form the sum 11 would lie somewhere here. Let's go ahead. Let's do the same with 2. 11 minus 2 is 9. So can I say it lies somewhere here before 10, which was first element's pair? Let's go one more step. 4. What is 11 minus 4? 7. Right? Where will 7 be? Can I say even before this 9? Yes or no? Everyone, are you with me till now? So what is happening is, if my first element that I'm fixing is going forward, its pair, its possibility to be found is going backwards. Like, for example, with 1, I might try this 15, but if this 15 minus 1 is 14 and we try to go back, that means this 15 cannot form a pair either with 2, 4, 6, anyone. Yes or no? I'll repeat what I just said. I'm saying when for 1, I check 15. 1 plus 15 is 16. So 1 plus 15, 16 is already more than what I wanted to find. So can I say checking 15 with 2, 4, 6 is useless? Yes or no? Because even with 1 plus 15, 16 was greater than 11. So with more value like 2, 4, 6, checking with 16, 15 does not make sense because it will obviously be more than 11. So simply, when for first element, its pair is here, for the second element, its pair is backward, for third element, its pair goes more backward, this points towards two pointers. One is moving forward, one is moving backward. Can you all visualize that? So whatever we are fixing first is moving forward, and its pair that we are searching is, we are trying to search it backwards, like its pair will be backwards. So this is a common pattern that we see. So if binary search points towards something like this, that if one pointer goes ahead, its pair which you are searching, your search space goes back, that means we can probably use two pointer here. Is that making sense? Because many people are confused when to use two pointers. That's why I'm pointing this out, this pattern. Repeat two pointer once again. Sure, I'll do that. Did you understand this? When we have 1 as first element, so we had to find two elements whose sum is 11, right? When we fix one of the element as 1, I need to find 10, its pair, which will be somewhere here. Do you agree? Same with 2. If I want to find its pair, 11 minus 2, 9, it will be somewhere here behind 10, because it's sorted. Like 10 will be ahead, 9 will be behind. Then when I go to 4, it will be 11 minus 4, which is 7. That will be behind 9. Do you agree? So as the first pointer, which is your fixed element, is moving ahead, its pair where it will be found is moving back. Do you agree with this? Right? So that points towards binary search of opposite pointers. That is, this will go ahead, this will go back. Let's use the same approach with the difference. Let's say we had to find two elements whose difference is k, and let's say k is 11. So when we fix y equal to 1, what do I need to search as its pair? Can everyone tell? Now we had to find x minus y is k. Find two elements whose difference is k. I've slightly modified it. So let's say first one is 1 that I fix here. What would be the second one? Its pair. Can I say it will be 11 plus 1, which is 12? Yes or no? If k is 11, it will be 11 plus 1, which is 12. So where will I find 12? Somewhere here. Let's look at 2. 11 plus 2 is 13. It will be ahead of 12. 11 plus 4, 15. So this indicates when this moves forward, its pair also moves forward. So this is 2 pointers which are moving in the same direction. Here the 2 pointers were moving in the opposite direction. These are two very common patterns that are there in coding. I'm not going into a lot of detail. So if you read 2 pointers, you will be able to put it into one of these two. And it's very easy to figure out if you go via brute force to binary search to 2 pointers. Okay. But is the idea making sense? Yes or no? How we can think about whether 2 pointers can be used here? Please repeat. Sure. The second one or even the first one? Second one, sure. So I have modified the question slightly. Now we had to find two numbers whose difference is k, right? Let's say k is 11, right? So let's say my first number is 1. First number is 1. Can I say my second number is 11 plus 1, 12? 12 will be somewhere here, right? So for this first pointer, my second pointer is here. Let's move ahead the first pointer, 2. 11 plus 2 is 13. So can I say if first pointer moved forward, here it was 12, I need to go to 13. Can I say it also goes forward? Not in this case, but if there was 12, 13, 14 also, then it will go forward, right? Yes or no? Similarly, when I go to 4, make it one more step forward. 11 plus 4 is 15. It again goes forward. So even with binary search idea, you are able to clearly see when first thing that I'm selecting goes ahead, the second thing also goes ahead. This is a common pattern, like though both the pointers moving in the same direction. When you start at the beginning, move the first pointer, then move this, then move this, then move this, then move this. This is a common pattern that you would have seen if you are coding for some time now, right? So, and this is opposite, when both starts at opposite end and they close finally. These two are the common 2 pointer patterns. Does that make sense now? Yeah, cool. Great. I think I have covered the different categories. There was one more that I can probably quickly cover in a moment. But any doubts here, let me know. How to code the odd even? Sure. The odd even one, the previous question that we talked about. Okay, I'll do that. let's take this as an example. So again, let's say L is 0, obviously, H is n minus 1. Then while L less than equal to H, that will be there. Find your mid, L plus R by 2. Do you agree with this much? This is common. Fixing L, fixing H, finding mid. Okay. Now first I need to check if mid is my answer. So if mid is my answer, neither its previous nor its next would be equal. So if A of mid is not equal to A of mid minus 1 and A of mid is not equal to A of mid plus 1, that means return A of mid. Do you agree with this? If neither the previous is same nor the next is same, that means they are not in pair. Yes or no? Again, as soon as you write this mid minus 1, mid plus 1, there are two corner cases that sprung out. What if I am at the beginning or what if I am at the end? So let's handle that separately. We'll do it at the top. That is, the first itself is not same as the second. That means first itself is single. And if last and second last are not same, that means last itself is single. Will you be able to do those two corner cases up? And then we'll start with L equal to 1, H equal to mid plus 1. Sorry, mid minus 2, whatever you want to do, right? Cool. Will you be able to do that? I'm not writing that, right? Is that okay? Okay, cool. So this is the case when we have found the answer. Now we want to check if we are on the left side or we are on the right side. So let me focus on the left side for now to determine if we are on the left side. So if my mid is even, if my mid is even and mid is same as the next, A of mid is equal to mid plus 1. That means we are on the left. Do you agree? If mid is even and mid is equal to mid plus 1, that means we are on the left. Or if mid is odd and it is equal to the previous, then we are on the left. So there will be an or. If mid is odd and mid is equal to mid minus 1, that means we are on the left. So there will be two conditions. Either we are on even and it's same as the next, or we are on odd and same as the previous. Will you be able to do that? The two conditions, right? And then if you are on left, move L, otherwise else move right. Will you be able to code it out completely? Yeah, okay, great. So again, as I said, just 2-3 things to take care of. LH, like checking if the current is the answer, and movement, right? So if you are able to get these two, then it's all okay. Okay, I think pause here. One more important question, I'll just mention it so that you can try it on your own. There is a common question where we are given a matrix which is row and column wise sorted. So as an example, if I have something like 1, 4, 6, 8, 3, 9, 11, 15, and 4, 12, 15, 18. Let's say something like this. And you have to find an element in it. Okay. So every row is sorted, every column is sorted, and you have to find a random element in it. There is a method which starts at here. Okay. I think it's discussed somewhere in arrays section. I will separately post its video link. But this is an important question which is asked a lot, and you actually need to understand why we are going left or why we are going down, those two steps, and why we are starting here and not here or here. So I'll post this question. Just make sure that you go through this and as much binary search as you want, right? Yeah, so you can start here or you can start here. These two are possible options. but not these two. And there is a reason for that. So you need to understand clearly why we do that, so that you're able to explain it well in the interview. Cool. I think we'll stop here. I think we have covered a lot today. So great. I think let's meet next, like tomorrow, and we'll see how it goes. Any doubts, anything? I'm still here for 5-7 minutes if you have questions. Topic for tomorrow, I'll inform, probably graphs. We also wanted to have a few resume and interview prep kind of sessions. So I'm not sure when we are going to have those. If we have that tomorrow, then graph will be shifted, or we'll start with graph. Okay, great. Okay, bye everyone then. Let's meet tomorrow. Cover the rest topics. Okay, sure. That's a relatively less arts topic. Sai, apart from Zor kind of questions. Okay. Yeah. Great. Bye-bye.